basically, if you want to optimize the queue, okay, you can use the model that you have depending on the assumption, right? So if you don't know the assumption, then you are going to use MMS. What is the meaning of MMS? MMS means you have only single line, right? And then parallel server.
Okay.
Okay. So don't forget a single line and parallel server. So if you compute with using that formula, okay, then if you compare it with multiple line, multiple server, what is the meaning of multiple line, multiple server? That means one line, one server.
So MM1.
Correct. M times MM1.
Okay. Yeah.
Okay. So in that case, the multiple line, multiple server, or M times MM1 is actually better in terms of queue length because, of course, the space is much bigger. Okay. So, but in terms of delay, it's not necessarily better because basically this is MM1. It's not parallel server. Correct? When you use MMS, the meaning is you have parallel server. So this is very important lesson because if you go in current situation, okay, people don't understand the meaning of queuing because they are doing serial server as if they thought this is parallel, right? So you go to government office, you even go in Petra, it's the same. They will, go from this server and then go to the next, right? So the number of server, for example, 10 person. But because they are using only serial system, it's basically the same as one server.
So one server do this and then the other do the other different thing. It's like not one single person can do all the stuff and
exactly.
that
Yes.
gives service to many other people.
Correct. So if you have one person can do all, okay, it's actually most of the time, not always, but most of the time actually faster because you can serve in parallel. Okay, so say you have a supermarket, okay, and then or an office. Each person in that office is specialized, highly specialized. Oh, I can do only accounting. Oh, I can do only personalia. Oh, I can do only for the cashier, for example. Okay. Oh, I will do only inventory. Right. So by specialization, that means you are creating serial server. Okay. But to make everyone must know everything. Right? Everyone must know everything. So whenever someone in need, for example, or the demand is high in certain areas, they will, even the one that do inventory, suddenly change to become cashier. Right? So in that case, the number of person, okay, who serve as a server is actually more efficient. Okay. So you are part of industrial engineering. So you think of in the industry, okay? So you start to think how I will make them, my employees, working as parallel server, not as a serial server. That is the big lesson in queuing theory, isn't it?
Yeah.
If you want to improve your system, don't make it serial. Always make it parallel.
So each independent server can go, can serve without waiting on the other server. So just do mind their own customers, right? Like So if I have a company, then like it would be faster if the, let's say, the call center, probably, like if it's a internet company, then the call center can solve a lot of problems, starting from bills and then the solving technical issues. It's faster.
Yes. So, but in the past, okay, people think that highly specialized will make a better worker because they are improving the speed, right?
Mm-hmm.
That is the creation of assembly line.
Yeah. Okay.
Right. So, but if you think in terms of queuing nowadays, okay, that kind of assembly line in 19th centuries is no longer exists so much nowadays compared to before, because the worker now is much smarter and can do a lot of things. Okay. In 19th centuries, it's like beginning of industrial engineering. Yes, probably that is true. But is it still true nowadays? I don't know.
Okay.
Okay, so hello everyone. So did you make your assignment for queuing theory?
I tried.
I tried.
I
Really,
tried.
sir.
I really tried, but I cannot find
Sorry. Yeah,
the number to go to the plot. So
I tried
I
to
really
use your
tried.
calculator, and yeah,
I use your
certainly
calculator, but find the L and the W, but I don't find anything else.
Which part is the difficult part there?
You said that
Oh.
lambda equal to rho, and therefore I became confused. What number that I need to put inside the calculator of lambda?
Oh.
So it
I
was like it's the question was like, we got the mu, right? The service time. The service time is one customer per minute. But and then is it the row is 0 to S, right? That was the question.
What is the question? Let me check.
I also didn't understand where to find the, is it the row, the lambda is 0 to
This one,
something,
right?
or
I think, okay, I will share my screen.
the 0 to something is the services
Is
number.
this the one?
Number of
Your assignment
yes,
is this one, right?
yes.
yes, this is the one. But yeah.
So we have rho is lambda per mu, right?
Yeah.
Yes.
So
Yeah.
then mu is given, right?
Yes.
Yes.
Is one customer per minute.
Mm-hmm.
Yeah.
So rho is set from 0 to S. S is the number of server.
Mm-hmm.
So you can set rho equal to 0, rho equal to 0 0.1, 0, 0 0.2, 0 0.3, okay, until S. S is the number of servers. So for example, your number of server is 2, right? Then rho is 0, 0 0.1, 0 0.2, 0 0.3, until 1, 1.1, 1.2, 1.3, until 2.
Oh,
Okay.
Until
Okay.
2. So
Yeah,
we
if
decided
S
to
is 2.
server by
oh,
ourselves.
so this, the MMS, the minimal is 2, the S is 2.
No, can be S.
No.
S
No, we
1,
decided
2,
it
3,
by
4.
1, 2.
Right?
Okay.
The
Right?
minimum is 1, I think.
So I put in here S is up to 10, right?
Yeah.
Yeah.
So in that case, you create the computation so that the row is in 0.1, okay, from 0, 0.1, 0.2, 0.3, yeah, 0.9, 1, 1.1, 1.2, and so on until 9.9 and then 10.
Oh my god.
Oh my god.
But that's Excel. It's just copy and paste what is my.
Yeah, yeah.
No, I mean like
Uh,
we didn't get what
So the
this
change, so the
statement
changing part
means.
is the row one. The changing part.
Row is changing, right? From A
Ah,
to S.
last night I thought
If you
the
know
number of
mu,
converted.
right? If you know mu, and you know that rho is equal lambda per mu, of course you can calculate lambda.
Ah,
Easy, right?
Yeah.
okay.
So
Hmm.
sir, the
Okay.
incremental is only 0.1, yeah. You said like
Oh, it's
from
up to
0 to
you.
good.
Yeah.
Oh.
Yes. At least 0.1. If you want 0.05, yeah, it's also okay.
Oh,
But allowed, right?
Oh.
So if you are
Okay,
lazy to make
okay.
it, so you put it 0.25, that's also okay.
It's
Right.
even more.
So,
Okay. Wait, let me try again then.
right. So I will extend the deadline for this assignment so that next week you can resubmit if you want.
Okay, okay.
okay.
I think I start to understand
Okay.
this homework. Okay. Thank you,
Right.
sir.
So it's just Excel problems, and I give you the answer anyway. So, right. So some
Yes,
will put
yes,
something
you
like
did.
this.
But I like last night
I
when
just
I reset.
I understand the explanation of the graph that like the lower line is the better line, right?
Yeah, yeah. The graph, that's the problem, right? So
Yeah, how do you
the graph, you of course you fill in the points in between. You make a graph. You fill in you make the point in between, then you make a graph
okay, yeah.
logically.
I see.
Okay. Anyway, I will extend your assignment up to next week so that you can revise.
Okay, thank you, sir.
No
Thank
problem.
you, sir.
Okay, so today we will this one, right? So we will discuss about Markov chain. Okay, the slide that I gave is a little bit theoretical. I hope you can bear it. So I'm searching my other slide. Okay, wait. Here it is. Okay, I will just share my screen. So this one is actually in simulation, but I will just show you. So I try to develop a Monte Carlo simulation, okay, of Markov chain. This is basically Markov chain. Okay, I have a certain initial state and I have certain transition probability, and I want to know how a token or agent move from state to state, and then I want to know what is the frequency visitation of each state, and then what is the time ratio for the state. So, and then I develop this Monte Carlo simulation of the Markov chain. So, okay, what is Markov chain? Right. So the slide is in Moodle, so you can follow. Okay. So Markov chain is basically a stochastic process, okay, with a certain special property that given the value of x in here is random variable, xk, k is the time, okay? So the value of xs for s larger than k are not influenced by the value of xu for u less than k. Wow, if you look at this, look like very complicated, isn't it? So, but the way you read mathematics is like this. Look at the notation of K and S and U, okay? K is current time, today. S is tomorrow. S is larger than K. That means tomorrow, day after tomorrow, and so on. U is yesterday and before yesterday. U is less than K. K is current. Okay, so what is Markov chain in that case? That means Markov chain is a model. Okay, stochastic means you have probabilistic in here. That the value of the future is contained in the current state. The past will not change the future. So many example of Markov chains actually being done in the field of science and mathematics and engineering. So I give you example is the financial education. Okay. Say, for example, you have a loan of 1,000 and interest rate of, say, 3% per month. This is the interest rate of what? Interest rate of credit card, right? Actually, interest rate of credit card is 3.6 per month. Say, and you don't have money, okay? So you pay only $20. Say you borrow $1,000 and then every month you pay only $20. The question is, when are you going to pay off your loan? So in this case, okay, in the beginning I put 1,000 and then the formula is simple, right? So the formula is basically the previous state, okay, 1,000 plus the interest, right? In here, C3 times C7 is the interest. Can you see it? And then minus C4, what is this? C4 is the monthly payment. Right? So your previous balance plus the interest minus your payment. That is the formula, isn't it? So then if you do it, what will happen? You will never be able to pay off your loan because your loan is actually increasing, never reduce. Can you see that? So yeah, this kind of system is basically Markov chain. Why? Because you see this, today, okay, the future, this is K times 1, right? It depends on today only. Today is time 0, right? The future is times 1. It depends on time 0. So the same thing, times 2, okay, month 2 is depend on month 1 only, not depend on month 0. Can you see that or not? Of course, this example is not really Markov chains because the probability is 1. So when we have there is certain probability to go to certain state, okay, then it becomes Markov chain. So in here is the example of deterministic. But you see that the value of tomorrow depends on today. That kind of system exists in many fields, right? Including finance, something like this. Okay. Until here, you have question?
So this is the formula?
The formula is just this. Can you see it?
Yeah.
So what is the meaning of this formula? The formula said that the future, tomorrow depends on today, isn't it?
Yes.
Okay, tomorrow depends on today. That is the formula. So I can give you another example of Markov chain in one dimension, huh? Random walk. So something like this. Can you see this? So initially you have 0 times 0, and then at time 1 depend on time 0 and certain probability distribution, which is based on normal standard inverse. So this kind of system is called Brownian motion or called Wiener process. Okay. So this is exactly Markov chain of one dimension. You see this, there is probability, right, to go to the next stage, and then that probability depends on only one step before. Can you see that? Look at the formula. The formula is one step before. So, of course, when you run this, you will see Brownian motion. Okay. So, similar to stock market, isn't it? So, you have any comment, input, question? I just give you example of Markov chain in the simplest Markov chain, which is in one dimension. In here, in this example, okay, this is called non-homogeneous Markov chain. Why? Because the probability changes every time step. Okay? The probability changes every time step. Okay? So, okay, let's come back here. So, the conditional future state distribution, okay, depends on present state only and independent of the past state. That is the definition of Markov chain. Okay. Next. Markov chain can be considered as sequence of random variables, okay, which correspond to the state of system. So if you want to model Markov chain, okay, you think in terms of discrete things. For example, if you talk about disease, okay, so what is the possibilities? Have disease or not disease, okay? Sick or not, right? Or you can have three states, healthy, OTG, orang tanpa gejala, yeah. So it's just under influence or actually sick. So every time, every situation that you can put it into certain discrete states, you can model it as Markov chain. Okay. And then a realization of that random variables, okay, will become a finite sequence of this one, x1, x2, until xk minus 1, xk plus 1. When I said xk here with small letter, that means the value. Okay. When I put xs in here with capital letter, that means random variables. Now, when you have a random variables, okay, when we say realization, that means we realize that random variable into real values. So I give you example here. In this Brownian motion, okay, the random variables is x, right? X equal, or xt equal to xt plus 1. I will put it in so in Brownian motion, we have xt plus 1 equal to function of xt, right? So that function is basically what? Xt plus normal 0,1. Okay, so this is the formula of Brownian motion. You look at this, that the value of the future, which is t plus 1, depends on only on current, which is xt. Now, when we realize this, okay, when I said realize, mean we put it into values, then you will see these values in here, in this Excel. Can you see it? I will show you the Excel. Share screen. So this value is one realization of that formula. So if I press F9, I create another realization of that formula. Okay, if I press another X9, I create another realization of that formula. That formula represents the random variables. These values represent the sequence. Okay, until here, is there any question? Or probably not question. What do you learn from this? So that I will know did you get it or not. Stephen.
Me?
Okay.
Well, I do get that this Markov chain is
It's a process.
it's like it's the probability, it has probabilities that is always changing.
Not always. A system with a probability that depends on the future depends only on current.
Oh, okay. So the future depends on the.
Okay.
So what happens next is based on what happens now.
Correct.
Okay.
Okay. So
Okay.
any system that the future depends on current but not the past is simple.
Okay.
Okay. So any probabilistic system that the future depends on current, not the past, that is called Markov chain.
Okay.
Okay. The probability can change or not change. When the probability is changing over time, that is called non-homogeneous. When the probability is constant over time, that is called homogeneous.
Okay.
I will share.
Oh, so that's why you give example with the
Non-homogeneous. Yes.
the loan is for the homogeneous because the rate of the what is it, the
probability is constant, which is 1.
Yeah. Okay.
Okay. So the one in random walk, the Brownian motion a while ago, the probability is changing over time.
Okay.
Okay. So when we discuss later on, I will fix the probability. I will not make it moving over time so that it's simpler for you.
Okay.
But remember the general definition of Markov chain first. That the probability is not always constant. Okay. At this point, I want to see the general view first. Later on, when we go to the constant, you will stick that, oh, Markov chain is always constant. It's not necessarily. Okay. Okay, let's go back to the slide. Okay. Now the probability, okay, the probability of one step, it's called transition probability. Okay, say at its point, Markov chain is in one possible state of certain probability. Okay, the change of the states in Markov, okay, is called transition. Now, for example, the current state is I. Okay, so in this case, xk, k is current, right? Xk is equal to I, and then the probability to go to the next state of j, okay, is given by this formula here. Xk, probability of ij from k to k plus 1 equal to probability of xk plus 1 equal j, given that now is xk is in state I. Can you see? Can you understand the meaning of this formula?
No.
No. Okay, I will explain. So this formula here, how to go to annotate? Okay. So this formula here, okay, this is the one that I want to explain. So this is the probability that you are currently in state I. Okay. If you want to go to state J in the tomorrow, okay, what is the probability? So the probability is P, this one. But remember, when we have the notation of this, that means currently, okay, K here is the current time. K plus 1 here is tomorrow. Okay. When I put the value K comma K plus 1 here, that means the probability keep changing over time. And the subscribe here, okay, Ij mean the probability from I to J. Okay, I will show you example in whiteboard. Okay, clear all. Say suppose you have the state, I put it into nodes. Okay, so I will call this A, B, C, D. And then in Markov chain, I will put probability from A to B, A to D, okay? And then C to B to C, and so on. Say, this is just a simple example. What is the probability from A to B? Then you will say, oh, the probability from A to B is 0.7. Then what is the probability from A to D? Of course, 1 minus 0.7, which is 0.3, isn't it? So from B to go to C, what is the probability? There is no other way, then probability is 1. The same thing here. From D to C, what is the probability? There is no other way, then the probability is 1. Then I want to put this into a matrix, okay? Then I will say, okay, I will have A, B, C, D, okay? A, B, C, D. Oh, what is the probability? Then I will say A to B is 0.7, and then A to C is 0.3, right? And then B to C is 1, and then D to C is 1. All the others are 0. So this matrix here is called transition matrix. So I will put it S or P. So this matrix is also called stochastic matrix. So that's why I put S here. Why? Because the sum of each row is always 1. Okay, what is stochastic matrix? Stochastic matrix is a matrix where the sum of each row is equal to 1, and the matrix is between 0 to 1. So basically probability matrix. Up to here, any question? Lilian, what did you learn? What did you just learn? Oh, Eugene, are you still there?
Yes, sir.
So what did you just learn?
Well, first thing first, it's the same like what you said in your talk about the future that depend on the previous events, the possibility and stuff. And also about the one that you just explained, I still don't really grasp it.
You did not get it yet.
Yes, I cannot say I cannot give you some explanation for that. I'm sorry.
Okay. So let's say I give you example, okay? Probably you don't get it because you don't have the example.
Okay.
Okay. So weather forecast. Okay. Weather forecast. If today is sunny, right? Tomorrow is cloudy. What is the probability? Okay, I will make that into a.
So today is sunny, and
Okay.
what's the probability of tomorrow?
So you have a 3 possibility of weather forecast. Okay, this is today. Okay, and this is tomorrow. Okay, so today is sunny, cloudy, or raining. Okay, tomorrow is sunny, cloudy, or rain. Okay, so if today is sunny, tomorrow sunny again, what is the probability? Give it.
1.
Well, not necessarily that.
50-50, right?
Okay, we'll make it 50-50. Say 0.8. Okay.
Okay.
And tomorrow, what is the, if today is sunny, tomorrow is cloudy, what is the probability? Keep any
0.2.
0.2. Okay. And then that just means this is 0, isn't it?
Yes.
Okay. So if today is cloudy, what is the probability tomorrow is sunny?
0.3.
2.2.
Okay, 0.25 if you don't like. Okay. If today is cloudy, what is the probability tomorrow is cloudy?
0.5.
Okay, 0.5. Okay, that means the total, this one is also 0.5, 25, isn't it? Because total,
Yes.
right? The
Okay.
sum here is 1. Okay. So if today is raining, what is the probability tomorrow is sunny?
0.1.
0.1. Okay. Whatever. This is your numbers. Okay. This is your number based on your observation over 1 year. Okay. So if today is raining, tomorrow is cloudy, what is the probability?
0.5.
Okay, 0.5. That means in here 0.6 or 0.4. Right?
Yes.
Okay. Okay.
So did you get? So this is example of Markov chain. Okay, this is the stochastic matrix.
Mr. Teknomo, Abel
Yes.
is trying to enter the class.
Where is Abel? Where is Abel?
He said it's in the waiting room.
Oh, Apple is still not here.
Abel is not here. Waiting room. Where can we get the waiting room? But, okay, where are we?
Until the probability.
Oh, in the whiteboard, right? Okay.
Yes.
Then if you look at this, okay, you have 3 nodes, right? If you look at this, no, you have 3 nodes. What is that? Sunny, raining, and cloudy, isn't it? Cloudy. Then from sunny can go to rain, from sunny can go to cloudy, right? Sunny can go to itself. The same thing here. Okay, from rain can go to sunny. The same thing, yeah? And can go to itself, right? Correct. So you can represent Markov chain as a graph or as a matrix. Okay, meaning the stochastic probability of Markov chain you can represent as a graph or as a matrix. So up to here, do you understand? You want another example?
Oh,
So,
yeah, this is clear, I think.
This is clear. Okay.
Yeah, thank you, sir.
so the stock, what is it? The
Stochastic process.
stochastic.
Example, if you don't like this SCR, I will change the name. Okay. I will change the name into, say you are modeling stock market. Okay. So what is the name of the, so if today is hold, right? Today is hold, tomorrow is buy, and then sell. Hold, buy, sell. Okay, the probability probably different, but anyway, this is example, isn't it? Today is hold, tomorrow is probably hold again. Okay, instead of buy, probably I need to change it into going up. Right?
So it's what I get here is probability based on event on the
Yeah.
base event.
Yeah, there is an event. Okay, so today it's in here. I mean, you hold it. There is no change. Okay, and then you mean going up. The stock price is going up.
You sell.
Okay.
You sell.
Yeah, going up. Probably you want to sell. Okay.
Yeah.
So down you probably want to. So using this, you basically you can model Markov chain. I mean the stock market. You can model it as Markov chain, isn't it?
Mm-hmm.
Mm-hmm. So as long as you get the probability, how do you get probability? You observe, okay, how many times going up, divided by the total observation, you get probability, isn't it?
Yeah. Mm-hmm.
Probability is just relative frequency, okay? So how many times going up, how many times going down, right? Divided by the total observation. For example, you observe 1,000 bar, 1,000 days.
Mhm.
So how many days going up? If today is constant, how many days going up? Of course, what we mean by constant is a certain period, okay, a certain value, right? Or if the value is just changing little only, I will consider that as constant, right? If the change is so much, then I will consider that as going up or going down, right? Okay. So once you understand that I can model anything, okay, into state, discrete state in here, right? And then I can put probability into discrete state. Then I model Markov chain. Clear, yeah? Now, if the probability keep changing over time, this is not constant, okay? That's called non-homogeneous, okay? If these probability values here keep changing, yeah? But if the probability are constant over time, that is called homogeneous. Okay? So I will show you back the can you see this?
Yes, sir.
Okay. So homogeneous, non-homogeneous transition probability, okay, currently at I, tomorrow at J, right? And the time is also changing, K, comma, K plus 1 in this value. Can you see this value? So that means non-homogeneous. But if the probability is independent of time, okay, look at the notation here, there is no time component. Okay, that means it is homogeneous Markov chain. The probability is constant over time. Okay, so from now on, we will only discuss homogeneous Markov chain. Okay, meaning the probability is assumed to be constant. But just remember, Markov chain is not always constant. Can be changing over time. Okay. Okay. So one of the property of Markov chain is memoryless. Okay. That means you start from x0, okay, and then x1 is 1, xi1, x2, and so on, until currently at xk equal I, right? And then tomorrow, here, the probability of tomorrow is actually at state J. So that is actually equal to this formula here. So regardless the past, I don't care about the past. Okay, look at I will know that the probability of tomorrow only depend on today, not depend on the past. Meaning it forget the past. The meaning of equal here is important. Equal means I forget the past. Whatever the past, I only remember today and tomorrow. Okay. Next, we will study homogeneous finite Markov chain in discrete time. That means the homogeneous mean what? The probability is constant over time. Finite mean the state is finite, not infinite. And then discrete, the time is also discrete, yeah, not continuous. Not real time. The time is 1, 2, 3, 4, 5. Right? If continuous time in 1, 1.1, 1.2, and so on, right? Real value. So the transition probability is stationary. Stationary means constant. Okay, the probability is constant, not time dependent. Okay, and then the state space is discrete. Again, the time is discrete time step. So our notation is becoming like this. Okay, so the probability of tomorrow at state J, while today is at state I, is just constant Pij. Okay. So next, we have what is called state probability. Okay, the symbol is Pi. Usually we put it into a vector, okay, pi. So what is this Pi? Pi is the probability that the Markov chain will be at state I at times k. What is the probability that the Markov chain will be at state I at time k? Okay, to understand this, I will give you example. This one. Okay. Can you see my screen here? So I generate a random number. Okay, can you see? Every time I press F9, the random number changing, right? And the transition matrix, that stochastic matrix a while ago, is constant. I can change because this is in yellow, I can change the value. For example, if you don't like 0.5, I can set with the 0.4. Then, of course, the sum must be 1, right? That means this one become 0.35. Okay. So then in the simulation here, if initially I'm in state 1, right? What will happen in the time 1? At time 0 is state 1. What will happen in the time 1? So I will still in time 1 again. Okay. So let's try if actually I make it 0.1 in here, and this one is 0.5 in here, and this is 0.4. You see this? In the beginning, can you see this simulation?
Yes, sir.
Okay. In this simulation, at time 0, I'm in state 1. In time 1, okay, I'm in state 2. In time 2, I'm in state 3. But once I'm in state 3, okay, just remain in state 3. Right? Can you see the movement of the state here? So if you don't like this, you can change this, the value, say 0.7 here and 0.3 here. Now the state is changing between 2 and 3, from 1 to 2 or 3, and then moving between 2 and 3. Can you see the simulation?
Yes.
Yes. So this is the example. 2 and 3, 1, 2, 3, the state 1, 2, 3 here represent in your stock is constant or going up or going down, right?
Okay.
Okay. So if you don't like 1, 2, 3, you can name it like the weather forecast a while ago. Sunny, right? What is this? cloudy, right? And then raining. Yeah. The same thing here, sunny, cloudy, and raining. Okay. You see? Formatting. Yeah. So state 1 is sunny, state 2 means cloudy, state 3 means raining. Okay?
Why did the state change when you only change the 1, 2, 3?
1, 2, 3. No, I just name it.
Yeah, you changed the name, right? But the state when you previously
When I
when you
change
put
this, the state is also the simulation changing because it's random number. So every time I press F9, it will change.
oh
Can
okay.
you see that? Okay.
Yeah.
So the transition matrix is their probability.
The transition matrix is the probability, and then because this is probability, so it keeps changing over time if you simulate.
Okay.
Okay. So initial state is 1. Say you don't want that. You want to initial state is actually state 2. Okay. Then it will go only 2 and 3. Again, every time it changing. And you see, oh, can go to 1 back. Okay. So you understand the meaning of Markov chain. Markov chain is basically you have a state probability. Okay. This one, the one that earlier I said, initial state, that is the what is the state probability that I am now in state 1. What is the probability that I am now in state 1? That is the meaning of state probability here. Okay, what is the probability that I am now in state I? So by putting into vector, then you will know what is the probability that I am now in state 1, 2, 3, not just state 1. I'm now in 1, 2, 3. So all the possible probability of all states. That is the meaning of stochastic vector here. Okay, so earlier we have a transition probability, okay, the C or S. That means this is the conditional probability that currently I'm in state I, tomorrow I will be in state J. Okay. So I already discussed about this. So this is also called a stochastic matrix because the sum is 1. Okay. If the sum of row and column is also 1, that is called probabilistic stochastic matrix. Anyway, this is not so important for you. So how to compute? How to compute Markov chain? What do you want to compute? What we want to compute is what is the probability of the states, which is pi I. This is what we want to compute. Okay. What is the probability that if today I'm in cloudy, what is the probability that tomorrow will be cloudy? What is the probability that tomorrow will be raining? What is the probability that tomorrow will be sunny? Given that today, what will be tomorrow? Okay, so it's kind of predictive, isn't it? So to compute that, Okay, you compute the total probability. The formula is here. Okay, this is the formula of total probability. That if I know all the conditional probability, okay, of I, then I can compute the probability of J. Okay, so in scalar you can compute it this way, but actually in matrix computation is simpler. Okay, I give you an example here. Okay, suppose you have this Markov chain transition probability matrix. Okay, determine the probability that P1 is 2, P2 is 3, and X3 is 1. If the initial probability is given this way. Second, can you compute the conditional probability of this one? And the third, can you compute the total probability of this one? So then the answer is this. So if you know the probability, so this answer is based on the on this formula that I give you a while ago. Okay, given the state probability at time k and the transition probability from k to k plus 1, okay, then the state probability is just simple computation of this. Okay, so look at the subscript, okay. I, when we compute, is only for I, not for J. Okay, probably I give you time to practice first. Can you compute this and then you compare with your the answer here? Can you try to grasp the meaning of this? Is it okay?
Yeah.
Still don't understand it.
With which part, Darin?
Yeah, to convert, like, which I have to take like that.
The formula, can you understand the formula?
Not really.
Not really. Okay, I will explain then. Can you see this?
Yes.
Okay. First thing first. Can you distinguish between transition probability and state probability?
No.
Oh, okay. Transition probability is the change from one state to another. For example, currently I am in state I. What is the probability to go to state J? That one is in the matrix. So example, if today is sunny, tomorrow is cloudy, what is the probability? That means transition probability from sunny to cloudy. Is it clear? That is transition probability. Transition probability means the probability of change of the state. Okay. So next is the state probability. What is state probability? State probability means what is the probability that today is sunny? What is the probability that today is cloudy? It's not a change, it's the state itself. Okay, so PI here represent the state probability. PIJ here represent the transition probability. PIJ and PI. Can you see the difference?
Yes.
Okay. Okay. Darren, what do you understand of state probability?
The probability of the state itself.
Okay. And what is transition probability?
The probability of tomorrow. Like that, the transition.
Yes, the change. Okay. That today is cloudy, tomorrow will be sunny. Okay, the change of the probability. Okay, so then you want to compute, okay, state probability of tomorrow, right? So here is the state probability of tomorrow, and this is the probability of today, and this is the probability of the change. Okay, so probability of tomorrow equal to probability of today times the change. As simple as that. Okay, so the most important here is the subscript I equal 1 until m. What is the meaning? That means you will compute for all states. Okay, for all state I, not just one state. So you need to sum all states. Okay, so this is exactly the same. I exactly the same formula as here. I just put it into simple. Okay, the state of tomorrow equal to the transition probability times the state of today. Okay, so then you want to decide what is the probability of this joint probability. Of course, you know the current state today is x2, okay, and then multiply by the from 2 to 3 and then from 3 to 1. Right? Oh, this one in from yeah. Then you can get the value. While in here, okay, you get the probability that currently you are already in state, okay, x1 is actually in state 2 already. Okay, what is the probability that x2 will be in state 3 and x3 will be in state 1? Then you are already sure, okay, the probability is 1, right? And then multiply by this change probability from 2 to 3 and from 3 to 1. Okay, the probability in here is 1 because you are already sure. Okay. Okay. Now, next, we can also represent Markov chains as transition graph. The stochastic matrix a while ago, we can show us transition graph. So this is actually equal. Yeah. The transition probability is equal to transition graph. Okay. Then you can calculate, okay, given the initial state probability V0 and the transition probability P, I can calculate Tn. How to calculate Tn? Okay, so this is the formula. Yeah. If I know P at times S and P times T, okay, then I can just multiply the two of them, okay, to get P of time T plus S. So this formula is called Kolmogorov-Kaplan formula. Okay. Now, based on this, we can derive of the actual computation of Markov chains. Okay. What? Tomorrow is equal to the transition probability multiplied by the state of today. Then, because this is a recursive formula, okay, based on that recursive formula and the Kolmogorov-Kaplan equation, we can derive this equation. This is the one that we use. Okay, state probability at times n equal to initial probability pi 0 multiplied by the transition probability exponent n, but then you transpose. Okay, so this is the code. So suppose you have this transition probability matrix and your pi 0 is this one. And I want to know what is the value at times n. Okay, so if I multiply, I just used that formula a while ago. You look at this formula. Okay, and then I will have the result that I can plot here. This is just in MATLAB. So then the result is something like this. Initially, okay, I have 0.3, 0.2, and 0.5. That means initially 0.2 around here, 0.3 around here, and 0.5 around here, right? And then over time it will change, but at certain point, you see here, probably more than 10, the probability distribution of the factor of the state will not change anymore. It will become a constant values, okay? Which is 26%, 32%, and 41%. Can you see that or not? So given the initial state, say for example, today, okay, so if you want to interpret this is, today is sunny 0.3, cloudy 0.2, and raining 0.5. Okay, this is the meaning of P0. And then I want to know 100 days from now, what will be the probability that will be sunny, cloudy, and raining. And that is the result. So sunny is 26%, cloudy is 32%, raining is 41%. Can you understand the meaning of this?
Still get it.
Okay, so given that today is what is the value of the probability, you can predict what will be the 100 days from now. If you know the transition probability. So the transition probability in this case is given, right? With this one. This one. This is the transition probability. Okay, give me feedback. What you understand and what you don't understand.
So on the previous one, on the practice, where is it?
Yeah, practice one a while ago.
The practice of the Markov chain. So number one, on the number one, it's the initial state probability distribution is 0.3, 0.25, and
0.45.
So that's the state probability for each
Correct.
state. For each, so for one, it's 0.3, 2 is
Yes,
0.25, 3 is 0.45.
correct.
Now,
This is
so the
Zero.
question is the transition from 2 to 3 and 3 to 1.
yes.
The transition,
The transition that state at times one will be 2, at times 2 will be 3, at times 3 will be 1. Correct. Okay.
well, okay. So that's 0.25 times
0.5.
Wait. 0.5 is from,
to 3.
I'm sorry, from which?
From 2 to 3.
2 to 3.
Correct.
Oh, okay. So that's the transition probability.
Yes. And then from 3 to 1. Right. The 3 to 1 is what? 0.35, isn't it?
Yeah.
Yes. Then you multiply all you get.
So from number 2, since the state is given, then
Yes.
the probability will be 1.
Correct.
Okay.
Okay. 3 is the same as 1 anyway. But okay, the known state is already known, so 1, then you put it as probability equal 1 also.
For number 3, it's if it's known with the process start with initial state of 2.
Okay. If you know, then there is no more probability, then probability is equal 1.
So what's the difference between number 2 and
Number 2 is you know also that is already 2 at this point.
okay.
Okay, so it's the same actually.
Okay.
The result is the same.
Yeah, the result is all the same. Okay.
Yes, because that is the if you know the state probability, okay, so that means number 2 and 3 is exactly the same, okay, but the difference is number 3 there is a clause telling that you already know the initial state. In number 2,
It is in the question.
yes, it is in the question. You put it into the conditional probability. So the meaning of 2 and 3 is exactly the same.
How do we get the probability from from state 2 to state 3? It's like you put it in the formula.
Yes,
Like
from 2 to 3, okay,
Mhm.
2 to 3, 0.5, you mean?
Yeah. From
From
2 to
the
3.
transition probability matrix, you will know.
Oh, from 2 to 0.5. Okay. And then from 3 to 1, 3 to 0.35 here. Okay.
Okay, that is
Yeah.
from the transition probability matrix.
Okay.
Easy, right?
Yes.
Okay, easy. Good. So, how about this one?
Hmm.
The meaning of this sample.
Okay. This one I'm
Still don't
still
get
not
it.
sure. I'm still.
Okay. Remember, Markov chains mean every time it changes.
Yeah.
Okay. I simulated a while ago, right? Every time it changes.
Yes.
Then the question is, okay, every time it changes, and then depending on the probability, so every time you run it again, it will become different values, right? But amazingly, even if there are different values, there are certain type of Markov chain that it will, in the long run, okay, in the long run, it will become a certain value.
So that's why starting from let's say that's day 10 to day 100, it's one line.
Yes.
Like it's a straight line, not going up and down.
Correct. Okay. So there are certain type of Markov chain, and not all time. Okay. This is a special type of Markov chain that it will become constant.
Okay.
In the long run, it will become constant. Okay. So it is amazing because you see, you have certain type of asymptotic behavior. It's an ideal condition. Okay. So this is an example of that Markov chain here, right? So if I have this Markov chain, okay, whatever initial value that I put here, okay, it will become constant. Okay. So it will become 26%, 32%, 41%. So the constant here is the one that you want to know, right? Given the assumption that the probability is constant, okay, within 1 year, okay, so what will be the value, the asymptotic value, the ideal value, the steady state value, okay, the long-term behavior. So look at the queuing theory last time. How do you get that formula? It actually comes from Markov chain. Okay, I did not give you the derivation, but you can read on your own in the book, in the textbook that we gave, in the reference, right? If you look at the derivation, it's based on Markov chain. What is that Markov chain? There is a constant value. And then that constant value, they derive it into formula, which is the queuing formula MMS and M1 and so on. Okay? So now we go to deeper of that queuing. Okay? Where that come from? That comes from Markov chain. You got it or not? Okay. So what we have what is called limit distribution. Okay. So given the initial state probability vector V0 and transition probability matrix P, okay, limit distribution or invariant distribution is the distribution of state probability V infinity as K is the time, right? K approach infinity. That is the limit, okay? What is the value in the long run? This is exactly the one that I showed a while ago, isn't it? The 26%, 32%, 41%. This is the limit distribution. Okay? Now, limit distribution is not necessarily exists. And if it is exists, not necessarily dependent on initial state probability vector. Okay? So, when the state probability distribution does not change in the next step, then we call this equilibrium distribution or stationary distribution. Okay? Then the recursive formula a while ago will become something like this. You see? Say, for example, if I have V0, okay, equal to V star, then whatever K, it will always the same. Can you get it? If I started from initial value, the initial value is actually the same as the limit distribution, it will not change anymore. Maybe I should give you examples so that you will understand. Can you see this? Can you see my, a while ago, this one? So I will,
Yes.
okay. So let's make it 1%. If 1% is negative, right? That certain, meaning your loan will be paid off at time probably 70, correct? So at time 70, you will be able to pay your loan. Okay. So now my question is, what is the monthly payment? If I pay 200, if I pay monthly payment is 100. Oh, now I want to get so that what is the monthly payment? Okay, so that it will become constant. Say if I put only 20, okay, it's 3% going up, right? If I put 100, it will go down. So then a certain value, say 75, still go down. 50, 30, 10, 30. So you look at this. If I pay initially, okay, if I have 3% loan and I pay every month $30, initial loan is 1,000, okay? Whatever I put the loan, it will not change. For example, if I started with 1,000, over time it will start always 1,000. Do you understand the meaning of this?
So you're not paying your loan.
No, you are paying your loan. You are paying $30 every month.
But
you're
the value of the loan not decrease.
Yes, your loan is never decrease, never increase. This is equilibrium.
So you're just paying, so you're
You are
paying
just
the
paying your
interest rate
interest.
every.
Correct. You pay
Okay.
your interest, okay, but your loan still remain the same.
Uh-huh.
Okay, that is the meaning of equilibrium. Can you see that or not? Okay, so back to Markov chain. You understand, yeah? When I talk about equilibrium, okay, okay, here, right? Oh, the sharing. So I'm talking about equilibrium distribution. Okay, when I started with 1,000, the fee start there is 1,000 initially. Okay, right? Then it will always 1,000. Okay, so initially I put the fee start here is 1,000. Then it will always become 1,000. Can you understand that? The meaning of equilibrium. Okay. So again, limit distribution exists. If limit distribution exists, then the limit distribution is the equilibrium distribution. Can you distinguish between limit distribution and equilibrium distribution? You don't understand. Okay, I will explain again. Limit distribution, okay, is the value of the distribution that is already not changing. So this is an example. Okay, initially 0.5, right? Okay, and then it keeps changing. Up to certain point, it will not change anymore. It's just becomes 0.41. So the limit distribution is 41.38%. Got it? That is limit distribution. Okay. So what is equilibrium distribution? If I don't start at 0.5, if I start at 41.38, okay, initially I already started with this value.
Therefore, there's no change at all.
Exactly, there is no change at all.
Okay.
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 Okay, you understand now.
Okay.
Okay. If initially I already started with that, it will not change. Okay. That's why if the limit distribution exists, then the limit distribution is the equilibrium distribution. Correct? Right? If the initial state probability is given x0, okay, and that limit distribution exists, then that limit distribution is the equilibrium. Clear, yeah? Okay, so again, initially 0.3, going up and down, okay, and then it will become constant, become 32, right? But if initially not 0.3, but 0.3218 already, it will not change anymore. Clear, huh? So that is equilibrium. Okay, so now how to compute the equilibrium distribution, right? So our interest is to compute the equilibrium distribution. Okay, so to compute that, this is the formula. This is the optimization formula, isn't it? Okay, what? You have transition probability matrix, okay, and then you transpose it, and then you minus with I. What is I? I is identity matrix. Okay, and then pi star is the one that you want to know, and then you multiply both to get 0, subject to constraint this one. Okay, so you can use Excel solver to solve this, or we can use linear algebra. Okay, if you use linear algebra, this is how you will get. So, this is the derivation, this is the final formula. Okay, so how do you get this? First, you put the matrix P and then you transpose. And then you minus with identity matrix of the same size. And then you add 1, 1, 1 at the bottom. Okay? And then you form also another vector 0, 0, 0, 0. Okay? And 1 at the bottom. Okay? And then this symbol means generalized inverse. How do you compute generalized inverse? This is the derivation. Okay? So if you have A times X equal B, how do you solve for X? Right? How do you solve for X? So you multiply both sides with A transpose. Okay? After that, what you will do, because this is already a matrix, right? Of a square matrix, then you can put it into multiply by the inverse, both sides. Okay? Something multiplied by the inverse become identity matrix. Correct? So that means this part, okay, is the actual left inverse. So this is what is called generalized inverse. So this part I put it here, okay? So become generalized inverse. With generalized inverse, you can actually solve any regression problem. Okay, now I will ask you to do a homework, this one, okay? You solve the Markov chain equilibrium using Excel based on left generalized inverse. Can you do it? Oh, okay. I will solve it now, and then you can practice. Okay, this will become your homework. Say you have your, I will Excel. Yeah, I will close this one. I will create a new Excel. Okay, screen. Okay. Say I have a new Excel sheet. Okay, so you have a transition matrix, okay, P, right? So you have transition matrix P. So let's say 3 by 3, okay? So let's put it T, and then I will name this P, okay? So you can set any value, 0.4, 0.5, 0.1, right? So that the sum, because this is transition matrix, the sum must be 1, isn't it? Okay, the sum must be 1. This is to check. Yes, 1. So here I put 0, I put 0.5, 0.5. So the sum again 1. Okay, and here you can put any number, 0.1, 0.35 or 3.4, and this one 0.45. 0.55. Okay, so then I have pi here. Pi here, pi 0. So again, you can set any value. Okay, so remember this is, for example, sunny, cloudy, and raining. Okay, again the same thing, huh? I put it here. This is sunny, cloudy, raining. Huh? So this is special transpose. Okay, so this is your input. These two are the input, right? And you will compute the equilibrium value. Okay, I will put 0.1, 0.7, then the sum must be 1. Okay, again, the sum must be 1 here because this is probability, right? So the sum must be 1, then this one must be 0.2 initially. Then you want to compute the what is Pn, right? This is what you want to know. Pn. Okay, and to get the Pn, how do you compute the Pn? Remember the formula a while ago? Pn, how do you get the Pn? The formula is this one, right? Can you see this? Pn is equal to P exponent n transpose times P0. Okay? So I have and then I have the recursive formula here, right? So what I will do? I have transition matrix, then I will have the P transpose. Okay? P transpose. How do you get transpose? Okay? I will have transpose there of P. Okay? So initially, you put like this, okay? And then control, can you put F2, function 2, and then shift control enter. There. You get the result of the transpose. Right? So I want to get P1. Okay, I will put P1. How do you get P1? Remember the formula? P1 equal to P transpose times P0. Right? Then I calculate that. P1 is equal to P transpose. So I will multiply M mult. Okay. M mult is a matrix multiplication. What do I multiply? P transpose and P0. Okay. Then I put this, I put it like this. Again, there I got the result. And you see this? This is the result of P1. How about P2? How about P2?
So we multiply we to the power of 2, right? The P trans the P for the P. The
Yes.
P.
So you can use the recursive. Okay. You can use the recursive. Okay. How do you get the recursive again? You multiply again and mult. Right? This P transpose. Okay. Let's name it. Okay. So this one I will put it as PT. P dash T. Okay. So that I will know this is P transpose. Okay. So multiply. Oh, this one I will put name P0 so that we will know. Okay, pi 0. Okay, so there, multiply of P transpose and P1, right? Correct? Then shift control enter, I got the result. P1, see? P2, this one, pi 2, right? How about pi 3?
I multiply P transpose
Correct. Okay, P transpose and
and pi 2.
correct. Very good. So easy, right? What? How about if pi 100? Oh no. you will do this so many times? No, there is a cure for this, okay? The cure is this formula. See? You exponent this, right?
Yeah.
Unfortunately, in Excel, you cannot exponent. Okay?
Cannot.
Okay, unless you multiply, isn't it? So,
Yeah.
okay, so then how to solve that? To solve that, I want to use this one. Okay, use generalized inverse. Okay, how do you this? How do you do this? Oh, PT minus I. Oh, let's make it, okay? So I will create the I. I is identity, right? Identity.
Yeah.
Okay, so
1, 0.
1, 1,
Yeah.
right? So this is all 0. Okay, easy, right?
Yeah. Okay.
Okay. Okay. So and then what is the formula here? P transpose minus I. Okay, so I will create in Excel P transpose minus I. So I will put it here. Okay, P
Yeah.
minus I. Okay, so how do you do this one minus this one, isn't it?
Yeah.
Okay, I copy. Okay, Control V. Oh, I got the PT minus I. And then what do you do? Next is to create J transpose. What is J? J is 111. Okay.
What is J?
J is 111. 1. J is
Oh, 1.
11111 like that.
Okay.
Okay. So then I will name that matrix. What do you want to name it? P. You want to name it P? Okay, so I will name it P. Okay. What is P? P is just copy of this, right? And then in the bottom, I put 1, 1, 1. Okay, so let's name it P. P dot. You see? Okay. Next, I need to form what? I need to form this one, 0, 0, 0, 0, and then at the bottom is 1. Right? So then I will do that. Okay. This one is the vector. Let's call this, what do you want to call this? G. Okay. Basically 0, 0, 0 at the bottom is 1. Oh, I got the G. Okay, so name it G, small g. Okay, now we have prepared already. Okay, we have G, we have P. So next we want to calculate the generalized inverse. Okay, so we need to get L. Okay, later on we multiply L with P to get X. Okay, so I need to get L. How do you get L? I transpose the A, multiply by the A again, and then I take the inverse, I multiply again with the transpose.
Transpose.
Okay?
So A here is P.
No, P.
P.
Yes. A here is P. Okay? So what I will do, I will get the transpose of P. So I will put P transpose. Right? So how do you get the B transpose? I just transpose. Okay, of P. Right? So I just transpose of P. be careful in Excel, you need to know the size. So if you transpose it, the size must be, this one is 4 times 3, now become 3 times 4. So you highlight exactly the same correct size, otherwise it will not work, okay? So F2, Shift, Control, Enter, there, you get it. Okay, so I got, I name it B transpose, right? So I color it again. What do we need after that? After we transpose, multiply by A. Okay, A in here is P, right? So I multiply now. So here is B transpose multiply B. So just multiply. What? B transpose multiply B. As simple as that. Okay, be careful with the size. Okay, when we do matrix in Excel, you need to know the size. The size is 3 by 4 multiplied by 4 by 3. So the result is 3 by 3. Right? There, you get it. Okay, so then what I will do is to get the inverse of that, right? Inverse of, okay, let's name it, what do you want to name it? 8, let's call it 8, okay? Name it as 8. 8 here. So inverse of 8. Okay. So how do you get the matrix inverse? M inverse, right? Matrix inverse of 8. Okay. 3 by 3. So there. You got it. Okay. So let's name it 8 inverse. Okay. Next, what you will do, after you inverse, you multiply by the A transpose, meaning that you multiply by B transpose. Oh, there, I will get the L now. L. Okay. What is L? L is this inverse a while ago, multiplied by B transpose. Okay. So there. I multiply, this inverse and B transpose. Okay, what is the size? This is 3 by 3. This one is 3 by 4. So will become 3 by 4. There, I get the L. Yay. Okay, finish. You get the L. So when you get the L, what you will do? You multiply by the right hand side. Okay, so okay, you multiply by the right hand side. That means the right hand side is this one, 0, 1, right? So there, I get the equilibrium. Okay, now I get P star equilibrium, which is L multiply of this L and this G. Okay. Then I got the equilibrium value. This is the final result. Oh, close, huh? Can you see it? So if I make a P3, it's almost the same as P star. This is the equilibrium value.
Just 1% of the raining.
Yeah. Okay, you got it. So this is your homework, okay? So anyway, I give you the answer already. So.
Oh my God.
Oh my God, what is that? Is it difficult? No, right? Just follow this.
It's well, it's not difficult, but it's hard to understand.
Which part is hard to understand? The mathematics?
The
The meaning?
it's not
The
well.
meaning is understand. Do you understand the meaning? The equilibrium, you understand the meaning of equilibrium, right?
Yeah, we're basically equilibrium. We find the equilibrium so that
Look at this, okay? If I copy this, what will happen? Okay, I copy this into the equilibrium value. Okay, look at this.
I think
Copy this
you are
into.
not sharing your screen.
I'm not copy. I'm not sharing. I'm not sharing. Look, if I copy this equilibrium value, the P0,
Yeah.
you look at P1, P2, P3 will not change.
Mm.
Can you see that now? Okay, so to prove that this is equilibrium, right?
Okay.
Okay, so initially you can say, okay, this is 7%. Okay, this is 50%. Okay, this one is, oh, this is too much. So what, maybe 40, 43, 3%, right? So, okay, it keeps changing, but eventually it will become equilibrium.
Okay.
Your initial value is equal to equilibrium, it's always constant.
Mm-hmm.
Okay, that's the meaning. So computation is just following the formula. What's the hard part there? Right? The computation is just following the formula. Okay?
So from all of these calculations, from all the computations, we are looking for the equilibrium.
Correct.
Equilibrium is the same with the limit.
Limit distribution in the long run. Okay? The equilibrium is limit distribution in the long run. This is the steady state condition.
So whatever number we put on the pi 0, it will eventually
equally the same. Oh, yeah, you understand. Very good.
Okay.
Okay, so I give you the formula to compute, and then I give you example how to compute in Excel, right? So you did it.
Okay.
Easy,
So
right?
in pi 0, we can put any kind of number.
Any kind of number as long as the sum is say 1.
Okay. So yeah, okay, yeah. So any number. So if I put like, let's say 1 divided by 3, like already
Okay,
like, so that's
let's do
30,
that. Okay, so
33.
1 divided by 3, right? You want
Yeah.
to put that. Okay, let's start with that. Okay, I will copy this. So then it will change drastically, right? But so I will make it in here. I will put the same. Okay, I will copy this, huh? Oh, okay, I don't want to change. I will copy here, and I will copy here. I'll copy here, right? So what is this? This is P4, right? This is P5. Okay, and this is P6. Oh, six. Okay, so you look at the value, initially changing, after that not change anymore. Can you see that? From 17 become 11, become 9, become 8, become 8, 8, 8.
So when it reaches 8, then it will always be 8. And then when it reaches 43, it will go 43 until the end. And
Yes.
then when it reaches 49, it will stop at 49.
Yes. So no, it depends on this. For example, you start with only 49, right? But this is already exactly that. And then here is you start with only 5%. And then this one is 1 minus this one minus.
Plus. Oh, yeah. Okay.
Okay, so that will total is 1. You see, it's not. It's still what? 7. And then eventually become 8. And here 43, 42, and then eventually become 43. Here going up first, 50, 50, and then 49, 49. Only when initial value is exactly as P star, then it will always be star. It's not just one of the state. Because one state, it depends on the other state, you know. So in Markov chain, you are thinking about the whole system, okay? Not just changing one, then it will always independently only one. No, it will think about the whole system. Okay? Changing one is actually will affect the others. Now, what will happen if I change the transition probability matrix? Instead of 0.5, now I become 0.4, and this is 0.1. Then, of course, the equilibrium change, you see? Can you see that or not? The equilibrium now become 14,
39,
47, no longer 49. Did you get it? Okay, so simple, right? Once you make this, so you next time you say, for example, 3 by 3 only. Okay, so then you can use this for any system that is 3 by 3. Okay, 4 by 4, of course, you need to make it again. Exactly the same method. Huh? Okay, until here, any question? So you know how, you know what is Markov chain, you know limit distribution, equilibrium, and you know how to compute Markov chain equilibrium. Okay. So next, limit distribution is asymptotic distribution. Okay, it can be start at any initial state distribution. It will always convert to the limit distribution. So the limit distribution is independent of the initial state distribution. We have what is called stationary distribution. What is this? It's a special initial state distribution, okay, that if you start from it, the state distribution will remain the same at the initial state distribution. The stationary distribution is dependent on the initial state distribution. What is stationary distribution in this case? The equilibrium. Understand? The term. Okay, this is example. Okay, let's put this example in the Excel, okay? And then we can plot. Okay. So in this Excel, oh, tell me what is the number?
Of which one, sir?
The transition matrix. Can you tell me what is the number?
0.4,
Right?
0.5.
0.14, 0.14,
Uh,
and then next 0.15, and then
Wait, oh, so it's random?
no, this one. I want to show you this one. This example.
Wait, oh,
0.2, 0.8, 0.5, 0.5. Okay, let's make it 0.
is it in the PowerPoint?
In the PowerPoint.
Oh, okay. Of course, I didn't see the PowerPoint. I
Can you see
just
this?
see the
MC
Excel.
computing.
Okay, 0, 0.2, 0.8. Can you read it for me so that I can. So this one is 0, 0.2, 0.8. Next, what?
0.8, 0.5,
Next, 0.5. And next,
0,
0. And,
0.5,
0.5,
and then the last one, the last row,
0.25,
0.25,
0.65,
0.65,
0.1.
0.1. Okay. So
26,
initial probability is up to you. Say I will put 1/3, right? 1/3. Okay. Then I can plot this, right? Okay, I can plot this. So insert line probably. There. Right? So this is the three values. Basically, this one is sunny, right? Cloudy, raining. And this is time, right? So the x-axis is time. Okay. So this is exactly the same as this one. And what is the limit distribution? 26, 32, 41. Is that correct?
Yeah,
So,
it's the same.
yes,
Yeah,
correct. Okay, 26, 32, 41. Okay. So you get the result directly in Excel. Okay, so now if you use the limit distribution as initial distribution, you will get stationary distribution. Let's try that. Okay. So instead of 33%, so I will copy this, right? There you get exactly straight line. Can you see it? Okay. The three of them are straight line. Okay, so this is stationary distribution. So can you understand the meaning of limit distribution, initial distribution, stationary distribution? See, right? Okay, so this is basically Markov chain finish up to this slide. Okay, the next is just naming, classification. So up to here, any question? So you can complete Markov chain, right? Not sure? I give you homework so that you can practice. Okay. Okay, next is classification of the state. Okay, so this is not really Markov chain, but this is like if you have this kind of Markov chain, let's give a name. Okay, because the name represents the behavior of the Markov chain. Okay, there is what is called periodic Markov chain. There is what is called aperiodic Markov chain, absorbing Markov chain, reducible and irreducible. So I want you to understand the meaning of this terminology only. Okay, so it's actually rather simple. So what is periodic Markov chain? Okay, a periodic state is the state that always being visited again in the process. Okay, so that means regularly there is a period that it will come back again there at certain time. So if you get the greatest common divisor of the k, okay, is always larger than 1. Okay, if d is 1, that is called aperiodic. So there is no period. That is called aperiodic, meaning no period. Okay, that means all the state, the period is equal to 1. Okay, this is just a name. So this MATLAB code is to compute the period using eigenvalues. Unfortunately, we cannot use Excel to compute eigenvalues, so you need to use a certain software like MATLAB. Yes.
Is this supposed to be? Are you presenting the PowerPoint now?
Yes. You did not see.
Only see Excel.
Okay. Can you see it now?
Yes. Okay.
Okay. So, okay. So I'm just reading from this slide. What is the meaning of periodic state and period? Okay. And then what is the meaning of aperiodic? Aperiodic means no period. Periodic means it will come back again. After, for example, a period of 3, it will come back after step 3. Period of 2, it will come back after step 2. In the same state, it will come back to the same state. Okay? So, okay, I'll give you an example in here. Okay? If you look at this, okay, let's try this in Excel, okay, so that you can see. Share screen. Let's try this in Excel. Oh, how to? Where is the Excel? There. The Excel, we change the transition matrix, right? So we change this to 0, 1, 0, and then this is 0, 0, 1, and then this is 1, 0, 0, right? So, and then the initial value is 0 0.1, 0 0.2, and 0 0.7. There you can see the behavior. Can you see it? Okay, the behavior now from state 1 go to, okay, 70%. It will moving, okay, periodically, isn't it? Say from raining, it will become sunny, and then it will become cloudy, and then become raining again, and then become sunny again, and then become cloudy again, and then become raining again, like that. Okay? The behavior of the Markov chains is periodic in 3. Yeah, the period is 3. It will never converge. Okay, if you look at the equilibrium, look at the equilibrium is 33%. So it will never converge. It will always move back and forth in a periodic period, in the period of 3. Is it clear now? Periodic. Okay. So if you start with 0, 0, 1 third, 1 third, 1 third, what will happen? Anyone can answer this? Anyone can answer this practice? what will happen if we change the initial value to 1/3?
Will be constant.
Correct. It will be constant. Okay, let's try. So let's try that. So we start the initial value with 1/3. Yeah, it will be exactly 1/3, so constant. Can you see the graph?
Yeah.
Yeah, constant, right? Okay, next. Yeah. How about aperiodic? So this is an example of Markov chain that is aperiodic. Okay, so this is the P. Markov chain is defined by the P, right? So if you know the P, okay, you multiply P square is a positive matrix. Okay, P3 is also positive matrix. And the greatest common divisor is actually 1. So in that case, you will get Markov chain that is aperiodic. There is no period. Okay, can go up and down. Okay, so you need to test if this Markov chain periodic or aperiodic. So you need to test. Okay, so how to test? You multiply the transition matrix. Okay, so up to n, P2, P3, P4, P exponent 2, P exponent 3, P exponent 4. We can see that the diagonal entry of P4 are all positive. Okay, so that means P4 are positive matrix. Then we may think that this is actually Markov chain with period 4, but actually it's not. Okay, the GCD is actually 1. Okay, the GCD is actually 1. Then this Markov chain is actually aperiodic. Okay, so next is terminology of sink node and source node. Can you see this? From A can go to B, can go to C, right? But from any other node cannot come back to A. That means A is a source node. B is absorbing state. Okay, from any node can go to node B, but cannot go out. So B is a sink node. Sink is where you put your water in, right? So do you understand the meaning of sink and source?
Yes.
Easy, right? It's just the terminology, okay? So absorbing state or sink state, okay, is once the process enter to this sink node, it will never be able to go out. Okay, the state, a state I is called absorbing if and only if PII is equal to 1. Okay, if you want to know which one, do I have a absorbing state or sink state, then you will see that the diagonal matrix, okay, have entry of 1. Obviously, if absorbing state, then it is always aperiodic. Why? Because once you enter, you cannot go out, right? So you check the diagonal element of the transition matrix. If there is 1, that state is absorbing state. Okay. Look at this example. Right. The diagonal entry is 1. Can you see it? This one is 1. So that mean this is a weakly connected network. Okay, from state one can go to state two. From state two can go back to state two, but from state two cannot go back to state one. Okay, do you understand the meaning of absorbing state? There's a sync node.
So we cannot go back
Cannot go
to
out.
past.
Okay, once you go in, you cannot go out. Okay, now another terminology, weakly connected network. Okay, if a network with a sync node or source node or sync component or source component, then it is a weakly connected network. You already know sync node, right? You already source node, you already know. What is component? Component on itself is actually strongly connected, can go from, for example, here in the left side, component one, from one can go to two, can go to three, can go to four. Okay, from each node can go to each other, right? So if a network from one node can go to any other node and come back, that is called strongly connected. Okay, now if a network have a strongly connected but only partial, only certain part of it, then it is called component. Okay, in this network, okay, this is a weakly connected network. Why? Because it has source component. Where is the source component? The one in red. And there is sync component, the one in yellow. Can you see that? From node 6 can go to node 4, but cannot come back to node 6, isn't it? Can you see? So the terminology, this kind of graph is called weakly connected. It's connect, but weak. Why? Because I cannot come back. If my home is in node 7, I can go to my friend in node 1, but I cannot go home. Okay. So a Markov chain is reducible if it has more than one equivalent class. The meaning of equivalent class is component. Okay. So when your network is weakly connected, then your Markov chain is reducible. Okay. So basically, we just play with wording. Okay. So I will say reducible is equivalent to 2. Unconnected or weakly connected. Okay. Reducible is unconnected, meaning you have a two part of network in one graph, or weakly connected. Weakly connected, I showed a while ago, something like this. Defined as a network with source node, sync node, or source component, or sync component. Do you understand component here? Abel?
What? What was
Do you
the
understand
question?
component?
Yes,
Yes. Explain to me.
it's component 1.
What is the meaning of component in this case?
So I guess the component that contains the sync node, a sync node.
No, component mean a network. Like component 1 here is a network where I can go from any node to any other node in that component only.
Ah, I see.
Okay. component 2 here is from any node in that component 2, I can go to anywhere in that component 2. From 7, I can go to 5, right? And I can go home to 7. Okay, component is a strongly connected network. What is connected? Strongly connected. Strongly connected means I can go somewhere and I can go home.
Yep.
Okay, that is a component. Clear, yeah? So when a Markov chain is either unconnected or weakly connected, they are called reducible. So example, when the Markov chain is absorbing, it must be reducible. Why? Because there is a sink node, right? Or when the Markov chain contains a source node or sink state, okay, then it is reducible also. Okay, so this is an example of reducible aperiodic Markov chain. Can you see it? Where's the, why this is irreducible? Because
It is absorbing.
huh?
Because it is absorbing.
Absorbing, where is the absorbing state?
From 5 to 5.
5 is not absorbing state. Okay, it's not sink, this is a source. Right? 5 in here can go to 1, but cannot come back to 5. Okay, it is reducible because it contains source node, which is 5. Right? So this part, itself is forming a component, isn't it? Because from 1 I can go to 2, I can go to 3, 4, and 6, and I can go home. From any node in this component, I can go to anywhere in the same component, can go home. But, okay, this one itself, node 5 itself is a component on itself. Okay, so there is 2 components here, right? So, but this is weakly connected. You see, from 5 I can go to, this is component 1, okay, and this is component 2. From component 1 I can go to component 2, but I cannot come back from component 2 to component 1. And you see that or not?
So is there no sync node then?
It's a sink component. Component 2 is a sink component. Right? It's not a node. It's a component. Why is component? Because from any node in this component, we can go anywhere, right? As long as within that component. Is it clear? The meaning of component, is it clear?
Yeah. Yes.
Yes, good. Okay, so the meaning of component is related to what is called strongly connected network. Okay, Markov chain is irreducible. Okay? It means it has one equivalent class or one component only for the whole network. Okay, so irreducible means there is positive probability that the Markov chains will move from one state to any other state in finite time step. Okay, so the network will be strongly connected. All states are communicating to each other. Okay, all states can be reached from any state, including itself. Okay, so to test it is irreducible or not, so you use this test. Okay, if I is identity matrix plus P is the transition matrix, and then you exponent to n minus 1, n is the number of states, okay, and it is positive, all positive, then the transition matrix is irreducible. Okay. Unfortunately, you cannot use Excel. So you can use Python, you can use MATLAB, any programming language, but Excel cannot do this. Well, you can, but you need to multiply until n minus 1. For small, yes, but for big, you cannot. Okay, so having that knowledge, now you have classification of Markov chain. Okay, there are two types of Markov chain. One is called absorbing Markov chain. What? Reducible. Okay. Second, we have what is called ergodic Markov chain, which is irreducible. So in within that ergodic, there are two types of subtype of Markov chain. One is called regular Markov chain. The other one is cyclic Markov chain. Regular Markov chain is irreducible, aperiodic, no period. Okay, acyclic, okay, is regular Markov chain. The second one is cyclic Markov chain, which is irreducible and periodic. Both of them are called ergodic. Okay, just name. Okay, so ergodic Markov chain is called communicating Markov chain, is one of the, okay, one of all of the states form a single ergodic set, meaning the chains, you can go anywhere to any other state. From one state, you can go to any other state. Okay. Of course, the matrix is irreducible. Okay. So again, you can have a regular Markov chain or cyclic Markov chain, yeah, depending on the period. So this is an example of periodic irreducible. Can you draw the graph of this? Can you draw the graph of this? Anyone want to share? Can you draw the graph of this periodic irreducible?
I'll try.
Okay, try. Okay. I'll stop sharing. It's just to know, right? Okay, so you have two nodes. Okay. So name it node A and node B. So you draw a, oh, you don't need to calculate the limit. I just ask you to draw the graph. Can you draw the graph? You have two nodes, A and B. Can you draw?
Use table.
No, draw. Drawing. Then you, node A, you encircle, you make circle. Yes, and then node B, you encircle again. Okay, very good. So from A can go to A, right? With probability of 1, right? Can from A to B? Cannot. Okay. No, I think your matrix is not correct. Your matrix is should be 0, 1, 1, 0.
So does it mean it can go from each other to each other?
Yes. So that
Okay.
from A can go to B, and then from B can go to A. Right?
But cannot go to themselves.
Cannot go to themselves, right? Correct. So your drawing was not correct. Yes, can go to B and then go to A again. Okay, that self loop is not correct. Okay, very good. So you see this from A have probability to go to B. Probability is 1. Then if you are in A, the next step will be B, correct? The next step will be A again. The next step again will go to B again. So the period is clear too, right? Correct or not?
Maybe.
Still maybe. Oh no. I will clear all my drawing. So your P is 0, 1, 1, 0. Is that correct? That means from A, okay, can go to B. And from B, come back to A. What is the probability? 1. Meaning sure. If you are in A now, okay, if you are in A now, the next step will go to B, right? And then the next step come back to A. That means the period is 2. 1, 2, right? What? Step A will have period of 2. Step B will have also period of 2, the same. So GCD of 2 and 2 is 2, right? Clear? Oh, next I will show you another example so that how about if your P is something like this, 1, 0, 0, 1. That is what Darren made a while ago. So how do you draw this?
So it goes to itself.
They
Go
can't
to
go to each
itself.
other.
Okay, go to itself, and it will not go to its other. So this Markov chain is reducible or irreducible?
Irreducible.
No, irreducible is connected. Strongly
Oh,
is unconnected, isn't it? Right? A is not connected to B. So if it is not connected, become reducible. Remember, reducible have 2 parts, okay? Weakly or unconnected. Can you remember that? Okay, if we said reducible, okay, there are 2 possibilities, unconnected or weakly connected. Yeah. Okay. So next, where are we? So the rest is just a example. Okay, irreducible, aperiodic, right? This is the example. Okay. So this is the example of what? Oh, okay. Can you see this? This is reducible or irreducible, periodic or aperiodic?
you haven't shared your screen.
I did not share my screen. Okay, I will share my screen. Always. Okay, how about this? What do you think? This is irreducible or reducible?
It's all connected.
It's all connected. I can
So
anywhere, right? That means irreducible.
Mhm.
So then you need to calculate the period. So there is no period in this case. The period of A is not the same as B, not the same as C, not the same as D. So in that case, can become aperiodic. Huh? How about this one? At least you should know. Okay, you cannot calculate the period. Is okay. At least you need to know how to compute the reducible or irreducible, isn't it? How about this? Is it reducible or irreducible?
Irreducible.
The one can go to 2. Yeah, it is irreducible. Yeah. Okay. Yeah, irreducible with some period. Yeah, period is 2. We'll come back. So actually, if you multiply the transition probability matrix, you can see the period. Right? So how about this one? Irreducible or irreducible?
Reducible.
It is reducible. Why?
There's one unconnected.
It
First one
connected, but it's
weak. It's weak.
it's weak. Okay, this is which node is that?
4-1.
Correct.
Oh, yeah.
So node 1 is actually sync node, yeah, absorbing, isn't it? Oh, very good. So I think you already know. Okay, node 4 is a source node. Oh yeah, node 4 is also source node. Can go out but cannot go home. And then node 1 is also sync node. So this is a double problem. Huh? Yeah? So it's reducible. How about this one? Reducible or irreducible?
Reducible.
Reducible because
There's node that not connected.
connected, still connected, that one. But there is
D to A is weak, and
yeah, it's weak, okay?
D is source node.
D is source node. Yes, correct. Okay. Oh, this one. How about this? Reducible or irreducible?
Irreducible.
Okay. Can go
I think yeah, irreducible.
irreducible. Okay. And you can see the period.
1, 2, 3, 4. Is it A? No.
Okay. So period of 2.
Period of 2. How? What? Oh, so the period is from
you see from
one node back to the node itself.
Yes. How do you know that this is period of 2? Look at the diagonal element of this. Okay. If all the diagonal elements are positive in 2 and 4, right? Then probably this is period of 2. Okay, so finish. Wow, we finished Markov chain in one lesson. That's very good. So next week, what we will discuss about? Oh, maximum entropy. Can you read first? Maximum entropy. Okay, that is very interesting.
Okay.
Okay. Oh, next week we have class, right?
No.
No.
Yeah.
Yes.
I think yeah. Okay. Yeah. Next week. Yeah. Yeah. We have class.
Okay, we have class. I mean, Idul Fitri is only this week, right? Not next week.
Yeah. Correct. I think so.
Good. Great. So, any input, any question about Markov chain today? It's not difficult, right? So you will have an homework to compute the Markov chain, huh? To create the Excel. And this homework is very useful for your exam later on, right? Because the exam is similar to this. I just change the number. Then you just input that and then you get the result, okay?
Okay.
Okay, so that's why you need to make it. Anyway, just make it 3 by 3. Okay. Okay, so then, so see you next week then. Thank you very much.
Thank you.
Yes.
Thank you.
Yeah, thank you. Lillian and Nyoto, you want to consult?
Yes.
Yes.
Nyoto.
Okay, wait a minute. Okay. Ooh. So, regarding the form, sir,
Which
we have,
you are still in the bus, right? Surabaya bus.
yes, correct, the
Okay,
bus.
Okay.
So I have thought, give it a rethought, a rethinking.
Mhm.
So this is the,
Okay, you want to share this?
yeah. Can you see my screen? So on the previous one, we didn't ask for the
Income.
income.
Right. So now you put.
So yeah,
Okay.
so I'm just making sure whether so I you said right, we can use queuing theory or even Nash equilibrium for this, for the,
If you want, yeah. If you want. That's
yeah,
Uh,
but I think I would like to give it a try for the decision making. So whether, based on the result of this survey, should the government continue this project or not?
okay.
So that's the decision based on utility, I guess, isn't it?
Can you try this one? I will share you in the chat. Okay. So this link, this is I usually give to my students to read first this tutorial, because once you have a questionnaire, what kind of analysis? This is like the basic. Once you have questionnaire, this is the step that you need to do, something like that. I mean, this is like the foundation. This is not really operation research, but this is like statistics. Can you check that website that I just put in the?
Yes. The spreadsheet example.
Yeah, yeah. Data analysis questionnaire, right? So you need to do single variable and cross tab. That is the first part. And then from there, you can calculate conditional probability. Or once you calculate conditional probability, you can calculate Markov chain already. Can you see it?
Yeah, this the pivot table, right?
Correct, correct. Okay. Anyway, read that tutorial. It's not so long. I think you can read in 15 minutes or 30 minutes probably.
Cross tabulation.
Yes, all in Excel. All of those are in Excel. So you can use Excel to compute. Right, and then I think I already gave you this one. The feasibility study that I did in Japan before. So this is like how to compute the bus. I think last time you already explained about it. So if you want to use queuing theory, tell me what do you want to use? Or if you want to use what decision making, so what do you want to use?
What is this? Scenario 1. Scenario. Ooh. Whoa. Okay. So we must find the. So we must find out the passenger per cycle.
Yeah, in this economic analysis, you try to optimize, right? So say based on the demand, okay, if you know certain route of the bus, okay, then you can start to compute okay, what is the gasoline price, what is the engine oil, tire, driver cost, right? Operating costs, and then you know the how many passenger per cycle. You can assume, you know, if you don't know, you can assume, and then the fare, and then you check whether this is actually profitable or not. If not, you add some subsidy from the government and how much is subsidy per year, for example. Okay. And then from there, you calculate, say, if you know the distance, right? Then total distance, how many bus finally you need. So basically, you can calculate, you know, how many bus do you need? Or if you know the passenger and you know the kilometer of this, right? So of course, the more bus stops, okay, you can add certain value of waiting time and so on. But you can still see the whole system. Can you see that or not? So basically, anyway, the Excel is also there. You just download, right?
I downloaded it, but I cannot edit.
Huh? You cannot do.
I cannot edit because I don't know. Click here. Edit anyway. Okay. Unable to read file.
Because you did not know. You click yes. If you trust the source of workbook, yes. If you don't do that, it will not. It's protected view, right?
Yeah, I already clicked yes, but it said that some formulas might be missing, so that's why I don't know.
Really?
But I don't know. I think the calculations is all correct. Still correct, I guess.
But you can enter.
Yeah, now I can enter the Excel.
Okay.
Can I? Is it like let me?
Okay, I understand because this is a very long time ago, 2005. So the new Excel probably does not read that.
Yeah.
Right. But in the seat bus, can you see it?
Yes.
Those are the two options, minifan or minibus.
Mm-hmm.
I compute it and then I compare. Right.
So the price of the minifan or minibus is you just assume.
I checked last time. This is 2006. I was still in Japan, so that price in Japan in 2006. Oh, I don't know. In Indonesia, probably different. So you can change instead of US dollar, you can change it to,
Indonesian rupiah.
okay? So that's no problem with that. I think in US dollar will not change so much, the price. So 20,000 US dollar is around how much? 300 million rupiah, right?
I think so.
Yeah, so it's more or less the same. And then 400 is like double of that, so 600 million rupiah.
I guess, but the bus that is being used for Surabaya bus
It's
is
big.
the big
Yeah,
bus.
that one is probably 1.2 billion.
Yeah, so it's around
Yeah.
90,000 to
Probably.
no,
Maybe 80,000.
80,000, around
Hmm.
80,000 US.
180,000 US dollar. Yeah, it's expensive, that one. But again,
So
because you are simulating, right? Practically your analysis is simulation. So you can simulate any if you want.
so we can even find like for example, from the calculations based
Mhm.
on the demand that we have,
Mhm.
apparently changing from from big bus to
To minibus, for
minibus
example.
is
Yeah, why not?
still feasible.
Yes. So, for example, of a big bus, but you need to compare. The basis is the current, right?
Yes.
Okay. And then you compare the scenario 1, scenario 2, scenario 3, like that.
Mm-hmm.
Okay. Of course, the base scenario must be the current.
Yeah. So for comparison, right?
Yes, yes, just for the sake of comparison.
The benchmark, I mean.
Correct,
Mhm.
correct, correct. So, and then after that, you compare, and then you say, okay, I need this one is better option. So you can start to publish. Right?
And how do I figure out the demand from like?
If you don't know, you assume based on your questionnaire. Can you check the demand?
My questionnaire is.
I don't think we have that kind of question.
You don't have that question. So I think you probably ask, for example, if the price is like this, or you ask like this, how often do you use bus if the price is like this and the situation of the bus is like that?
Oh, so is it like this question? So it's the continuation of this. Wait, let me share my screen.
Okay.
So this one is like, are you willing to pay for the facility that you will get, like the free Wi-Fi and so on and so on?
Yes, yes. But how often are you doing it? If, okay, for example, I'm not using bus right now. Okay.
Yes.
Using bus. But if I give this facility, for example, oh, I wait only 3 minutes or I wait only 5 minutes, and then the price is this much. How often will you use this service? Once a day? That is represent demand, right? For example, your questionnaire distributed to 100%, okay? And then 50% of them say that I will go every day. That means 50%, say your sample is 100%, represent the whole population. Okay, say of how many million is population in Surabaya? Okay, that means 50% of that population will go to that kind of demand, assuming linear, assuming your random sampling is valid. Of course, otherwise you need to assume something. Otherwise, you will not. You need to study the whole population, meaning you sample the whole population of Surabaya. That's ridiculous. So you need to do sampling. if the facility is like this, you explain the facility. This is if the facility is like I give you 3 minutes waiting time, and the price is 15,000. How often will you use in a week? And then next is if tunggu bus. Say if now 15 minutes and the price is how much? Another 15,000. How often will you use bus for your daily activities?
So it's a different question. It's a different section then.
So this kind of question is called stated preference, meaning it's not real, okay, but that represents the demand, right? So you can always ask their opinion. Or you can make a table, okay? This kind of service 3 minutes, how much? 5 minutes, how much? Okay. 15 minutes, how much? 30 minutes, how much? Okay. And usually you make the price reduce when the service is bad, right? And then the price increase when the service is bad. So that you will see the crossing, you know, between the price and the service.
Can we do that in this Google form? Wait.
I think we must make a new one, so we don't need to use like the free Wi-Fi or the more comfortable chair, but just focus on the waiting time.
Similar like this, similar to this free Wi-Fi. Okay, but instead of 1, 2, 3, that is the one that you tell. Say frequency once a week, 7 times a week. Okay. Based on the frequency, you can instead of 1, 2, 3, you can say 15 minutes, 10,000 rupiah per ride. Okay. And 1 hour, say free. Right now it's practically free, right?
I think so. Yeah, around 3,000 rupiah.
So 1 hour but free compared to 30 minutes. Say how much? I don't know. So then from there you try to make a combination, and then they start to check how frequent they will use. Okay. Certain people will not use at all, you know. They prefer use car, whatever it is. Then it's okay. Then you will know how many percent is actually using car anyway. How many percent actually using bus, right? And then among those who are using bus, how many percent is actually changing because of the time, because of the price? And then the price now you compare with the income, then you get certain knowledge, right? So you will say, oh, because their income is high, then they are sensitive, they are insensitive to price. Or their income is low, then they are sensitive to price. That's usually the case, right? So the questionnaire will help you to find the demand. You know? Exact demand, but percentage. When you multiply by the total population, you get the demand.
Okay. So for this form, it's better if we focus on the waiting time, right? Not just.
I think you focus on the distance and waiting time, because why you need to know the distance, right? The preference, state preference, in opinion only. How long you will walk from your home to the bus stop? Then, when you create the bus stop along the way, you plot the area, okay, the circle around that, and then how many housing you can calculate, and then per house, for example, 5 person, then you get the population of the coverage of that bus stop, right? if you know the population, you multiply by that percentage, then you know the actual demand.
So if I, let's say, uh, using the maps.
Okay, say open the map.
So there's one route that goes from,
From Bumur Aceh,
where's my, no, it's near my house.
okay,
So the last bus stop is around here, I think. So this is the south part of Surabaya.
okay,
So this is Mer, Jalan
Okay.
Mer.
okay,
There's one route that goes from here, the end of the road, to I think around here, Kenjeran.
yeah, okay. So
And
when people use bus, okay, how they go from their home or their office to the bus? That is
they walk.
distance. They walk, okay, or they use becak, for example, right? Then you know the coverage, okay, meaning this is the bus stop, okay. The coverage is around how many kilometer or how many meter surrounding. They will not walk 3 kilometer, right? They probably will walk, say 1 kilometer. If they use becak, probably 1 kilometer. If they walk, probably around 500 meter, right? That means the coverage is around 500 meter from the bus stop.
And around that 500 meters, how many person live in there?
You open it, you zoom it. Okay, example, you zoom it again. Zoom. One more zoom. Can you see how many housing? There, you can see the house, right?
Yes.
Yes. So from here, you can see the housing. So that housing, you can assume one house, 5 people on average. Right?
Okay.
Okay. So if one house, 5 people, then how many house surrounding that area that represent the population? Oh, if that stop is actually near university or near the mosque, near attraction, okay,
Mhm.
so then you need to generate how many members of that mosque or how many church or the university or the school. Of course, high density, right? Instead of
Mhm.
So the bus stop actually should be located near certain attractions so that the number of people who will use is high.
So if it's here, then yeah, I think
So you just encircle there, how many, you can just guess, no? How many house or how many attraction there. Okay. So from the area of the mosque, for example, how many people are actually using?
let's say 100 people.
One mosque that big is probably 1,000 or 2,000. So then suddenly high density, you know. And then, of course, the demand, right? The demand from your questionnaire will get certain percentage. Say, for example, only 10% of them actually use bus. Then 10% times 1,000 or 2,000, you get at least 20, right? From that stop alone, per day or per hour, I don't know. So the unit must be clear, okay, so that you will know how to represent your demand.
Okay.
Okay, clear, right? something that you ask eventually converted into numbers that you eventually you can estimate. Okay, you will say not accurate. It doesn't matter accurate or not, you know, because people demands keep changing over time anyway, right? But you need to get an intelligent guess. Okay, science is basically intelligent guess, right? You know, it will not change so much. It will not change from 1,000 to 10,000, for example. It will not change that much. So if your estimate is 1,000, probably it will change 2,000 or 500. That's okay, right? Up to 4 times of the standard deviation probably is very bad, but well, still okay. Okay? It will not go 10 times. Your guess will not wrong that much. Okay. So, is it better to have certain guess rather than no guess at all, right? Oh, that is what science is. Okay.
So back to the drawing board with the questionnaire, and then
Yeah, and then you analyze. Okay, you get the conditional probability, the Bayes theorem. You have it there in my website. You can check. Okay. Oh, I think I did that questionnaire for bike and what is that? I forget. That was in 1990s. Oh no, this one is for park. Park, right? Public park. This is demand of public park. No?
yes.
Yeah, this is talking about the demand of public park. Are they satisfied or not? And then in the Bayes theorem, I think I used the old study about bicycle.
Wow.
Using car, new car or a second-hand car. So depending.
Okay.
Okay, so if you know the conditional probability, you know you can calculate the Markov chain also, you know, right? Basically, transition probability is conditional probability.
How about that, Lilian?
Huh?
Okay.
Oh my God.
It will never finish if you talk with me, so you decide to limit yourself.
Yeah.
Okay, otherwise it will never finish. Okay,
Okay.
like this. All what I said to you are suggestion. Okay, the purpose is to inspire you, not to limit you, not to make you obey me. You decide on your own. Okay?
Okay.
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 Okay, Lilian.
Lilian, congratulations to become the head of the HIMA.
Wow. How do you know?
I think you are the only candidate. Okay. So see you then next week.
Okay. Thank you,
Okay,
sir.
thank you, sir.
Bye-bye. Yeah.
See you.